So what do you know about momentum? What do you guys already know about momentum? What is it? Momentum? Sure, John.
As the energy left in an object as it's continuing to move.
Okay, the energy left in an object as it continues to move. What kind of context do we usually use the word momentum? If you're talking about this leftover energy.
Inertia.
Okay, something to do with inertia. I mean, we're kind of just throwing some buzzwords in there.
Massive force.
I'm talking about context, though. Give me an example where you might use momentum. Sure, Joe.
Like a truck or something that's rolling down a hill, something that has a lot of mass behind it.
Okay, so when we use the word momentum, we kind of invoke in that imagery of high momentum means it's hard to stop. It has a certain motion to it, and it's really has a lot of inertia. It's hard to change its state of motion. Okay, so then we might say it has a lot of momentum. And part of that, we say it has a lot of energy because we look at the truck when it runs into like a car. The massive momentum from the truck well overcomes the momentum from the car, or something like that. So we kind of associate energy with that. So as we develop our use of these terms to be more precise with the use of these terms, I want to focus more on the inertia part than the energy part. Okay, energy is going to be a little bit different, but let's just look at the momentum part and the inertia. So let's start with this. I want to look at our Newton's laws. Okay, we said that, let's just say we have one force. Okay, just for example, one force acting on an object, and so that should lead to some sort of acceleration for that object that has a certain mass, right? And from our kinematics, we know that for a certain amount of acceleration, you get essentially, well, here, we'll do it like this. V equals like a V naught plus AT, right? Let me go ahead and take this, kind of rearrange this. And we're going to say that this is like V minus V naught equals to AT. So that in order for the velocity for an object to move, there must be some acceleration on it over some amount of time. And we got this pretty much based on, for constant acceleration, our velocity versus time graph, or actually just, sorry, I should say our acceleration versus time graph. If it's constant, this is flat, right? And if it's flat, then we set that the area under this graph, this would be a change in velocity, right? And we can go vice versa. We could say that if you look at the velocity versus time graph, the slope of this line is our acceleration. Okay, so let's look at what the math language looks like here. We would say that if your acceleration is the slope of this velocity versus time graph, then your acceleration is the derivative of that velocity at any particular time. Right? And again, the main difference, the main reason why we use derivatives instead of just some sort of versus an average acceleration could be some net, oops, right? That's really the difference between a derivative and a not derivative. When you look at a derivative, you can look at the instantaneous rate of change of velocity over time, as opposed to if you just look at a net change, then you're looking at an average. Okay. So then what does the language or the math, syntax or convention or whatever you want to call it looks like here, then your integral of this function, which is your acceleration, over a bunch of little time steps will equal to change in velocity. Okay. So what this mathematically is doing in terms of, if you were to draw an analogy to the derivative is looking at the slope at a particular instant in time. What the integral does is it takes the area of an instant in time and adds it up over a bunch of instants in time. You take it and you chop it up into a bunch of tiny little rectangles and you add them all up, and that's what this does. Okay? The integral symbol is the summation of all those little areas. Okay, all the little areas. That's your Riemann sum, right? You're adding up all the little pieces. Okay, so let's look at this. Here's this. That gave this. And here we have F. F is MA. Here's A. So what happens if we put the M in there? So if I take my V, my delta V equals to AT, I'm going to leave a little gap here. And I multiply both sides by the mass. Then essentially what I get is this kind of M delta V equals to F times T. That means that, and this should kind of make sense, if I apply a force on an object for a certain amount of time, it should cause it to accelerate. As it accelerates, that should result in some net change in velocity. And so this, we can rewrite this as mv minus mv initial equals to ft. Okay, and this is what we call momentum. That's the left side of this equation. And this, loosely speaking here, right? I haven't really done the calculus part yet, but loosely speaking, then this is the impulse. The impulse is what leads to a change in momentum. Okay? Yep.
So is momentum just MV or is
Momentum is just mv.
not MV minus
No. So when we take the difference, that is the impulse. So in other words, your impulse leads to a change in momentum. A momentum is a state, right? You have a certain mass, you have a certain velocity, you have a certain momentum. If your momentum changes from one thing to another, you must have had an impulse act on you in order to result in a change in momentum. Okay? So that's kind of how the vocabulary works out. Okay, so when you apply a force for a certain amount of time, like imagine for a second, you know, all the stuff we've done in chapter 5, 6, 7, 8, the force has always been constant. It is constantly pushing on something. You constantly lift up a block. You constantly let the block fall. But what if you have a situation where you take a baseball bat and you hit a baseball, right? It's the interaction is not smooth. It is not, I mean, it's continuous, but it's not constant, right? It's not constant. So what we want to do is we want to be able to describe what's going to happen to the baseball without having to calculate what the force is like at all moments, right? Maybe we can experimentally gather that, but we don't want to. We need a way to find out what the net effect is after we add up all the effects, right? In other words, another way to think about it is, as you take the bat and you hit the baseball, you don't want to have to do the kinematics of the baseball at like every millisecond, right? You don't want to have to say, oh, the acceleration is this much, so now I take the initial velocity and then I multiply by my millisecond with my acceleration, and then I go to the next one and the next one. You don't want to have to do that, right? And so this is how we can do it. So how do I change this graph to represent this equation? What do I do? What is the graph for this guy? What do you guys think? Well, what did I change from here to here?
You added M.
I added M.
sides.
That's it. So instead of A and T, I have MA and T. That's the only difference. Right? And so that means that if this is a constant force, right, then the area under this graph for a certain amount of time, this is my delta mv, my change in my momentum, right? My change in my momentum. Okay, the symbol that we will use to represent momentum is P. Okay, P is momentum, so you can say delta P. P is momentum. Because we can't use M. M has already been reserved for mass. Yeah, so we're going to use P. So, this area under the curve, right? Okay, so let's try this. How would you write the integral that represents this? Okay, just try and compare, right? Just try and compare. If this was the integral that represented the change in velocity, which is the area under this graph, what will this integral look like? Integral of what? Yeah, Chris. F dt. That's it. You've done it. You now know impulse and momentum. We're done. Oh, yeah. Okay. Any questions so far as to P, momentum, impulse? Yep.
You did explain that graph one more time.
Yep. So if I apply a force, if this is a graph of what my force is on an object over time, so like I have my book and I'm pushing on it with a constant force, okay? And assuming, of course, there's only one force, so maybe not thinking about pushing on it, because sometimes we think of friction and stuff like that. Imagine you have like a satellite in space, and there's minimal gravity, it's in deep space, there's no gravity on it, and you only have the thrusters on it, and the thrusters push on your satellite, right? As time goes on and you constantly push on it with a certain amount of force, this is how your momentum will change over time. You will change by whatever the area under that graph is. So for however much time, right? So if you apply 10 newtons over 1 second, you now have 10 newton seconds change in your momentum. Okay. So if you look at the way the units work out for momentum, it is measured in a Newton second. Okay. Now you can't compare it back here. It's meters. It's like a kilogram times meters per second. Well, newtons is a kilogram meters per square second. So the per square second cancels out with one of the seconds, so you end up with newtons or kilograms times meters per second. Here, I'll write it out. Right here, if you look at these units, you have kilogram meter per second, right? If you look at what a newton second is, it's like a kilogram meter per square second, because that's a newton, right? MA, mass times acceleration, and then you times a second. So this is the same. as a kilogram meter per second. It's the same.
I'm also just a little bit confused how you went from that equation to that.
From this equation to this graph? Well, does this graph make sense for this equation?
Uh-huh.
So we said that if you take the area under this graph, we kind of, when we first started doing this, we kind of used the geometric description of it. We said it has a base of t and a height of a. So if you do base times height, it's kind of like your change in velocity, right? And so that's how we decided that it's the area under the curve. From a more calculus perspective, that's what this represents. So from here, I just went from here to here by multiplying both sides by mass. And so then it should be the same as if I just took this and multiplied by mass. And that's what I did. Just multiplied by mass. Okay? Okay, this impulse, we use the symbol J. Okay, J represents impulse. Be careful about how you distinguish impulse from momentum. Impulse represents the change in the momentum. Okay? It is how your force is applied over a period of time. Momentum is kind of an intrinsic value of the object itself. Some mass times velocity, right? Mass times velocity. It is important to note that when you look at momentum, momentum is relative because it's mass times velocity. Well, how do you know what your velocity is? Velocity is comparative. If an object's moving 10 meters per second forward, how do you know whether you're going 60 meters per second forward or backwards or whatever? It's just that that other object is going in a certain direction faster than you, so it has more momentum in a certain direction or has less momentum in a certain direction. Momentum is, I say it's intrinsic, but I say that just to mean that it's kind of like a property of an object, right? Mass is really more the intrinsic property, and again, since velocity is relative, you can always pick a reference frame where an object's momentum is 0. But then it just means every other object around it has a different, relative momentum, right? So momentum, just keep that in mind. Momentum is relative. It is also worth noting, sorry, this stupid faucet gets in the way. Since force is a vector, that means momentum is a vector. That means impulse is a vector. Because velocity is a vector, all of these are supposed to be vectors, 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 right? They're all supposed to be vectors. We derive this using this graph, kind of looking at it as if it were one-dimensional, just to kind of establish the understanding of it. But you can create this graph in the x direction, and then you add it to the graph in the y direction, do it in the z direction, and then you have your net momentum, right, using trig. They're all vectors. Okay? Any questions? Okay, so let's look at how this works. How do we use moment? Oh, sorry, go ahead.
Is J equal to momentum as well?
So J is equal to the change in momentum. Yeah, if you want to write that out, you can actually write it like this. Impulse equals the change in momentum. Okay? So some application of this. What it essentially means is that if you can determine how long a force is applied on an object, and you look at the graph of that behavior. So imagine for a second, again, the baseball hitting the baseball bat hitting the baseball. You might have a force versus time graph that looks like this. Okay. It initially hits the ball, and then as the ball starts to elastically remove itself from the bat, it gets shot away, right? So you might have a smooth curve that kind of looks like this. Okay. So what we're saying is, if you can add up this space underneath, you can determine the change in the velocity of the ball. You can determine the change in the velocity of the ball. Again, velocity is a vector. So that means that if you have the baseball bat, let me not use a baseball bat. Let me use a soccer player kicking a soccer ball. Okay, so you got a person with a really long leg. Just soccer ball comes down. Okay, and he kicks it. Here's the foot. Kicks it, and then it goes back up. Okay. Let's say for a minute that it's like a perspective view. The foot's sticking out. If the soccer ball's coming down with a certain amount of speed, okay. Let's say this has a certain mass. Let's just say it's like, actually 1 kilogram is a really heavy ball. So let's say it's like a half a kilogram. Okay, that's not too bad. Half a kilogram coming down at like 5 meters per second. Okay, if it's coming down at 5 meters per second and the soccer player kicks it upward and then it goes upward at 5 meters per second, what you need to determine from this is that the initial momentum, okay, it's a vector, meaning you have to keep in mind which direction you're going to choose as positive or negative. It is initially going down, which means it is 0.5 kilograms times a negative 5 meters per second. So it has an initial negative 2.5 Newton seconds of momentum. Okay. The direction matters for momentum. Because in order for it to go from being going downward to going upward, it has to accelerate upward. It has to change velocity from pointing down to pointing up. So if you look at the final momentum, it is still half a kilogram, but it is now going 5 meters per second up. It has 2.5 Newtons seconds of momentum. Okay. So what is the impulse on the ball? Be careful about that. What is the impulse of the ball? What is the net change of momentum? It was 2.5 down, now it's 2.5 up. That's 5. Okay, so if you work it out mathematically very carefully, J equals the change in P, which is equal to P minus P initial. So that's 2.5 Newton seconds minus negative 2.5 Newton seconds. And so this equals to 5 Newton seconds. Okay. To be specific, this is up. There's 5 Newton seconds upward. There is a direction associated with impulse. Okay? So you'll see that as we do momentum and we do these problems, they all involve usually more than one object. Okay, it's kind of weird to talk about impulse. Well, there's usually some sort of interaction going on. Something pushes it, something hits something, and then you have some net change in motion. Okay. Any questions so far distinguishing impulse momentum? Okay. So again, later on in the year, okay, after first semester is over, you guys have derivatives under your belt. You'll get a little bit of integrals under your belt. Pretty much all we really need is, once you guys get familiar enough with derivatives, integrals are actually very straightforward. They are anti-derivatives. It's like whatever the derivative of something is, the integrals is to go backwards. It's a little more complicated than that, but effectively, without really understanding the meaning behind it, that's what you can do.
Okay.
It's kind of like what the outcome is. And so then you might have a forcing function. What if you have a force on it that is kind of quadratic or logarithmic or something like that? Then you can figure out what the net change in velocity is going to be based on the function itself. Okay. If there are no questions, we're going to move on to a couple special cases. All right. Let's look at the case of a collision. Okay. So here's the convenient thing about momentum and collisions. If you have two objects colliding, you can always choose a reference frame where one of them is stationary. Okay. So for now, what we're going to do is we're going to look at a collision, which we're going to call a perfectly inelastic collision. Honestly, I think the perfectly can be omitted. Usually when you see something say it's inelastic, that has a very specific meaning. Okay, so imagine for a minute that I take a ball of silly putty and I shoot it at like a stationary block. The idea here is your object, let's say whatever, your silly putty is shot at a block, and the idea here is afterwards they are stuck together and they move together. That is the idea of an inelastic collision, is that when they start, they are two separate entities with different velocities, and when they are hit afterwards, after the collision is complete, they're moving together. So you can think of it like an accident where the two objects, after they collide, they don't separate. They get stuck, like a rear ending or something like that, or whatever. That kind of collision. Okay, so let's analyze it. Let's say this is M1, this is M2. Okay, and this has some velocity v initial of 1. Okay, and then this is, there's no velocity here, and then there's some v final. Or here, let me do this. Let me put the v final. Okay. So what momentum lets us do, and the reason why it's sometimes called a conservation law, is when you have collisions, the law of conservation of momentum states this. It's pretty much a combination of Newton's first and third laws. It says that, well, I guess you can put it like this. In the absence of external forces, a system will conserve its momentum. Sorry, my left hand. Okay, it will conserve its momentum, meaning that the momentum should not change for a system if there are no external forces acting on it. Okay. So why might that be the case? Here you have this object, and it runs into the second object. There is a force that they're applying on each other, right? They're interacting. So if this applies a force on this object to the right, it's going to gain momentum. Why would this lose momentum? What law implies that this should lose momentum as it adds momentum to this? Exactly. For every force, there's an equal and opposite force. Newton's third law. So if you have this graph acting on the second object, this graph must necessarily also act on the first object in the other direction. So no matter what, whatever the area here is that's adding to the second object, you must lose it from the first object because you have an equal and opposite reaction acting in the other direction. Right? So that's really why this works out. Pretty much just because of Newton's third law. This cannot apply a force on this object to push it forward without being pushed backwards by the same force in the other direction. Okay. So by this logic, then, the sum of the momentums, which is equal to initially m1 v naught 1. You notice that if this is stationary, if v naught 2 is 0, then this must equal to the momentum at the end. Right? And so therefore you can figure out how fast the object will be going at the end. Okay. Now we all have a pretty common visualization of a collision. One object runs into another object, right? That's not necessarily what has to define a collision. A collision is when two objects interact. Okay, so objects don't necessarily have to interact by a collision. You can have interaction from friction, two objects sliding past each other. Okay, so as an object slides past a second object, it will transfer momentum, right? If you have gravity pulling on two objects, if the Earth is pulling on the moon, you know, as the moon falls towards the Earth is transferring momentum, so the Earth pulls forward towards the moon, right? As the moon gains momentum in one direction, the Earth must gain the same momentum in the other direction. That is also an interaction, not exactly a collision from our, you know, standard understanding of collisions. That's just because by collision we usually mean there's some sort of contact force or something like that. But as long as there's an interaction going on, the conservation of momentum must be true. Okay. The same can be done. Yes. This is M1. And this is like V naught 1. I'm just trying to identify the different, the different masses. Okay, let's look at another kind of collision. Another collision that we might have. So, hold on. Let me think. Okay, well, all right, let's just move on. So let's look at another example of a collision. Okay, here's a pretty common kind of collision. Remember that momentum is a vector. So let's just say if you have this coordinate system. Okay, and you have a ball that's coming in. Let's say this is 2 kilograms coming in at 2 meters per second. And you have another ball coming down. And this is 3 kilograms moving at, 5 meters per second. Okay. And again, we're going to have an inelastic collision. Okay. If they have an inelastic collision, I want you to determine the vector representation of the final velocity. The vector representation. So give me the I and the here's the I direction, here's the J, right? Give me the I and J of where the, like, I don't know, whatever. They combine, right? Where'd it go? Give it a shot.
It's you to do horizontal vertical, right?
Yeah,
I'm doing
I was just realizing, so that J is not impulse, that's the J direction in terms of IJK kind of vector notation, right? This is the X direction unit vector. If you're not sure what to do from here, try this. What is the momentum in the X? What is the momentum in the Y? Yep. At the what? It doesn't matter. Just knowing that they have an inelastic collision is all you need to do. But that doesn't really.
How do you figure out the
Yeah, this could be offset. Maybe they hit over here, maybe they hit over there. It doesn't matter because if they have an inelastic collision, they must move in a certain direction. They must.
You can just grab it. Draw it out. You want 3 and then waiting for that. Like, you would do a triangle where it's like. So then you can say, find the angle below the top of X is usually measured from. Oh, okay, yeah, we can do it again. Yeah, you can do
If you're trying to do angles on this, you shouldn't really need to know any angles for this. If we're doing just vector representation. I tried to do vector representation to make it easier, quicker.
I think you found the magnitude, you found the angle of it.
How do you get the magnitude?
I might be wrong. Can you just do Pythagorean theory? And then put in some.
Yeah, so don't do Pythagorean. Go one step back. So you have the x component, is the x component in the I direction, and then you have the y component, the y component in the j direction. Do you remember vector notation? You have like whatever the value in x times unit vector I plus whatever happening in y times unit vector j. You know, it was like, I think it was chapter 2 or 1 or something. Chapter 2. No, maybe it's chapter 3. Alright guys, let's go ahead and move on. So, in order to do this in vector notation, okay, first let's look at the momentum happening in the x. This has initially no momentum in the x, the top one. Okay, this is what's providing the momentum in the x. So you have 2 kilograms times 2 meters per second, which gives you 4 Newton seconds of momentum in the x direction. In the y direction, you have 3 kilograms going down 5 meters per second. So you have 3 kilograms times negative 5 meters per second. That gives you negative 15 Newton seconds. Okay. So to determine the momentum afterwards in the x direction, right, then it's still 4 Newton seconds. So if you want to determine the velocity, you're going to take your 4 Newton seconds and you're going to divide by the total mass of the system, right? You're dividing by the total mass. So you're going to divide by 5 kilograms, so you get 4.4 meters per second in the I. And then just kind of seeing ahead that it's going downward, you're going to have 15 divided by 5, or 3 meters per second in the J. Okay, so this is how fast it's going in the x direction or I direction. This is how fast it's going in the y or j direction. Now if you want, yep.
Can you explain how you do that again?
Yeah, so it's just this should equal to the two masses times the final velocity in the x direction. Does that kind of make sense? Whatever the momentum was before should equal to the momentum after in the x direction. So the momentum in the x direction at the end is this. So I just solving for the x part. 4 divided by that sum. Yeah. Okay? Again, you're going to find that for these problems, the math is not going to be the most complicated part. The hardest part is making sure you put everything in the right spot, picking up all the values that you need to know, so on and so forth. Now, some questions it might ask would be, what is the magnitude of the momentum? The magnitude of the momentum, you will have to use Pythagorean theorem on this, right? So the actual momentum, right, the actual magnitude of this will be 5 kilograms times this thing. Does that make sense? This is your net velocity, your actual velocity, not broken into parts, right? And then your mass is just mass. Yep.
Are we allowed to use the velocity final equation up there?
You can multiply all this by 5, right? Multiply by the mass, and then that gives you the momentums in each of the directions, and then you still have to do Pythagorean theorem on it, right? Because you're still trying to find the magnitude. These are just the components. Either way, it's either putting the 5 out here or you're putting the 5 in there. It's kind of the same thing. Okay? All right. So aside from collisions, sometimes you can have explosions. Okay, explosions are kind of the similar type of problem. You are conserving momentum So an explosion is when you have, instead of two objects coming together, you have one object coming apart, right? So for example, let's say you have like a potato, and after it explodes, it breaks up into three parts. You have one part going up, with well, let's say this is like a 3 kilogram. It's a hefty potato. It's like a 7-pound potato. Nice beefy potato. Okay, so you got half a kilogram going this way, and this is going like 2 meters per second. Okay, and then you have another piece going this way. Okay, and this is 1 kilogram, and it's going, say, 3 meters per second. Okay, so then you should be able to figure out which direction and how fast that last piece is going. Determine V in, we'll do it in vectors again. The vector notation of V for the last piece. The third piece. It is stationary. It just sitting there and poof.
Is there a ground to?
A what?
Is there a ground to prevent things from going down?
No. This is in space. Space potato. can you not see that? Is it too light with the pencil? Kind of. Which part? All of this little stuff? Okay, so how to determine the path of this French fry, I suppose. We're just looking at, again, some of the momentum in the x, some of the momentum in the y. Now, in this particular case, initially, if you really want to be explicit about this, the sum of the momentum in the x is 0, right? Oh, sorry, you're right. Okay. Initially, the sum of the momentums in the x is 0. If it is stationary, and again, this is all relative. We are choosing our system just to analyze this little space. Remember Feynman talking about the checkerboard? We're just looking at this little part of the checkerboard, right? And so afterwards, you have this piece going off to the right with a certain amount of momentum, 1 kilogram, times its 3 meters per second, which means it must be offset by whatever the x component of this third piece. Right? So that means that the x component of this third piece, that momentum must equal to 3 Newton seconds, which means this is equal to that mass of the third piece, which is 1.5 kilograms, times its velocity in the x. Okay, and so then you get Vx3 equals to 2 meters per second to the left. So one thing you kind of have to be careful of, depending on how you want to do this, is, again, like we did before with forces, you can kind of arbitrarily pick a direction for your momentum that you're trying to calculate, or arbitrarily pick the direction of your force, kind of like we did with friction. So if I just say, like, I think it's going to go this way, I'm kind of assuming it has a negative x component of momentum. And so I already inherently in the setup of the equation include the minus. So in the end, even though my answer is positive, it means it's positive in the direction that I indicated it was going to go, right? So just be kind of mindful about if you're doing this with just the magnitudes, be mindful about what the direction it was supposed to be, right? Kind of like this exact same with what we did with forces. If we include the minus signs as we do any vector calculations, then what we end up with for the answer is always going to be the assuming it is in that direction. Okay, so then we're going to do some of the momentums in the y direction. Again, that's, sorry, that should not be a capital P. It is supposed to be a lowercase p, don't do capital P. Capital P is reserved later on for power when we get to energy, so it should be a lowercase p. So the piece that went upward, that's half a kilogram, going at 2 meters per second, minus the momentum in the y for the third piece, right? And so then the momentum in the y direction for the third piece is equal to 1 Newton second, which is equal to 1.5 kilograms, so on and so forth. And so I get my velocity in the y for the third piece is equal to 2/3 meters per second. And this is going to be down. Okay. So if you do a vector representation of the velocity of the third piece, it should equal to 2I minus, or sorry, I guess it'd be negative 2I minus 2/3 J meters per second.
We can use x and y, right?
If you're doing vector notation, you would never do negative 2x because x is not the variable x, right? This is really specifically the notation you would use is the unit vector I represents a vector in the x direction. Unfortunately, it's like I'm trying to help you guys understand the meaning behind it, but contextually, you really shouldn't relate I with x. Because, like I said before, sometimes you have multiple reference frames overlapping, and so they have their own IJKs all rotating, and then you have your inertial reference frame on the outside of all of those rotating things, and that may be what you want to use for x, y, and z, right? So really just think of I and j as two perpendicular vectors, and that's just describing the length in that direction. Okay. Yes. Yep. It's not always minus. Minus, it depends on how you set up your diagram, right? In this case, I'm choosing positive I this way, positive j this way. And so if my positive I is to the right and the object is going to the left, that's why it's the negative 2. And since it's positive j up and the object going downward, that's the negative 2/3. So your positive and negative is all relative to your coordinate system. Okay, so chapter 9 is, let's see, 221. It's like 16 pages. Okay, it's not a whole lot. So we're only spending about a week on this, and then we'll start energy next, like Wednesday or Friday or something like that. So it's kind of a short unit. It's only one chapter.